Please, let's go around the horn, and I'll assume if you give me a go, you've got no instrumentation problems. Booster, go flight. Retro, go flight. Fido, go flight. Control, Telcom, go. GNC, Ecom, Capcom, go. Surgeon, go. ONP, go. ASD, FAO, go. Network, go. You got everything up? Go.
Hello, I'm Ian Christie, and this is Terranauts. So, it would seem to me that if we're going to talk about leaving the planet, the first topic that we need to cover is the means of doing so. And so far as humans are concerned, there really is only one way to get off the planet, and that is on top of a rocket. So, the first episode in the Terranauts Guide to Leaving the Planet is called Rocket Science. In this part, I'm going to talk about the history of what we now call a rocket and how it's related to, but different than, things like jet engines and guns and bombs, because it is related to those things. This will get us up to the very early part of the 20th century. In part 2, we'll talk more about the development of what we would recognize as modern rockets that have been taking humanity, or at least human creations, off the planet for about the last 80 years or so, when you get right down to it. Now, a quick disclaimer. Given the nature of the listener base of this show, I know that many of you probably know a lot more about this topic than I do. It's entirely possible that you will be frankly horrified by the shortcuts and generalities that I am about to take. Fair enough. Please do not hesitate to provide me with constructive advice on any egregious errors that you feel I have made. But please also do bear in mind that the purpose of this episode is to make the very complicated science of rocketry accessible to people who find it fascinating, but who have chosen not to make their living studying it. So, let's start by making this really simple. There are basically two things you need to know about getting to space on a rocket. The first is that there is no air in space. The second is that a rocket really just is a bomb with a hole in one end. There, done. See you in a couple of weeks. Just kidding. Let's dig a little deeper. The first fact, while obvious, is important for a couple of reasons. First of all, because there is no air in space, we can't use any mechanical mode of propulsion. There's nothing to push against other than our own spacecraft. So we can't use propellers or paddles or anything like that to move in space. We have to resort to what is known by physicists as a reaction engine. This is a fancy way of saying that we need to make use of the principle in physics that was first, or at least most famously, written down by Sir Isaac Newton in 1687, and which is usually rendered as, for every action, there is an equal and opposite reaction. Now, all of that may sound kind of technical, but the fact of the matter is that you have probably created a reaction engine yourself. Certainly you have, if you have ever inflated a balloon and then let it go. When you blow up the balloon, your breath is contained in the pressure vessel of the balloon. It is under pressure, and when you let go of it, the air is squeezed out through the opening. Because the air squirts out one end of the balloon itself moves in the opposite direction. The air is relatively light and moves fairly quickly. The balloon is proportionally heavier, so it moves slower than the air, although quickly enough to impress your kids or your dog or maybe surprise your aged relatives. Because there is no way to steer the direction of the exiting air, the balloon flies in a random pattern until the air is gone. But at any moment, the balloon is always moving in the direction opposite to the air that is exiting the balloon. In addition to the balloon example, there are a lot of different ways to create a reaction engine. Some of you may have experience with the compressed air and water variety, where air is pumped into a vessel, let's call it a plastic pop bottle, that has been partially filled with water and turned upside down and stoppered. And then when an overpressure is established in the bottle, the stopper is released or forced out, and the water is expelled out the bottom of the bottle and the rocket is propelled upward. Now, obviously, as impressive as this might be to a crowd of neighbors and kids, it's never going to provide enough thrust to get off the planet. In fact, so far, we have only really found one kind of reaction engine that is capable of doing that, and that is the chemical rocket, by which we mean something that uses a very rapid chemical reaction, known as combustion, to create a large amount of expanding gas that it then directs into a stream in one direction to generate thrust in the other direction. The important thing about a rocket is that it needs to carry all of its reaction products with it. In rocketry terms, these products are usually referred to as fuel and oxidizer. It is this fact that separates a rocket from its reaction engine cousin, the jet or turbojet engine. Jets are based on the same principle of combustion under pressure, followed by rapid exhaust of the combustion gases. The main and important difference is that a jet engine breathes in air in order to obtain the oxygen that is needed to burn the fuel. It does this by spinning turbines to compress a large volume of air into a combustion chamber, where it is mixed with jet fuel before being ignited. Turbine engineers refer to this process poetically as suck, squeeze, bang, blow. In fact, an awful lot of the technical engineering development of jet engines has gone into, and an awful lot of the machinery in a modern jet engine is devoted to, the first and second step, that of sucking in enough air and compressing it enough to generate more and more thrust. To some extent, it's actually fair to say that a modern high-performance jet aircraft, like a fighter jet, is really designed around and really limited by the need to scoop up massive quantities of air and compress it into a tiny volume. Now, rocket engines, on the other hand, skip the suck step entirely because they carry both the fuel and the oxidizer with them, so there's no need to try and obtain oxygen by scooping it out of the air. This is, of course, necessary for a rocket because, as we have already noted, there's no air in space. So, rockets go straight to the squeeze step. Similar to the development of modern jet technology, a lot of development of modern rocket engines has been devoted to this step because, of course, the more fuel and oxidizer you can compress into a small space, the more gas, and hence potentially the more thrust, you will get when you ignite it. We'll talk a bit more about the challenge of doing this without also causing rapid, unplanned disintegration events in Part 2 of Rocket Science. For now, let's summarize by saying that if we're going to leave the planet, we are going to need a reaction engine that is driven by chemical combustion, and we're going to need one that not only brings its own fuel, but also its own oxygen with which to burn the fuel. Interestingly enough, such rockets have actually been around for quite a long time. Although there's a bit of controversy about exactly when the first rocket appeared, it seems safe to say that they were certainly around by the late 1200s in China. It's a little bit hard to figure out exactly when rockets appeared, because what we would call a rocket was really only one of the uses of what we now call gunpowder, and those uses are a bit jumbled up in the literature that survives from the time. So, since gunpowder is the original rocket fuel, we should digress briefly to talk about that. For the record, gunpowder is a powder consisting of some combination of sulfur, charcoal, which act as the fuel, and saltpeter, which is potassium nitrate, and which acts as the oxidizer. It was discovered in China sometime around the year 900. Gunpowder is relatively light, and it's pretty much inert if you don't get it close to a flame or a spark. If you put it in a pile and light it, you get a very bright flame that is difficult to extinguish because it burns even in the absence of air, since it contains its own oxidizer. As early as the 10th century in China, it was being used as an incendiary to spit fire at enemies and to deliver fiercely burning packages attached to arrow shafts. But pretty soon somebody figured out that gunpowder had another interesting property. It's true that if you put it in a pile and light it, you get a serious amount of flame, but if instead you put it inside some kind of container or vessel, and then you contrive to light it, you get something else. You get a bang. In other words, if contained in some way, that rapid combustion becomes an explosion. It also turns out that if you tune the constituents right, generally by increasing the amount of saltpeter, you can increase the speed of combustion significantly, making it much less of an incendiary compound and more of an explosive one. Now, there are really three ways that you can use this effect. You can, for instance, simply enclose the powder completely in a vessel that holds the pressure until it fails, in which case you have invented what will become known as a bomb or a shell, or in small doses, a firecracker, which apparently was actually a fairly common use for gunpowder during the Song dynasty in the 11th and 12th centuries. Or you could enclose the powder in a vessel with a small hole in it, and when the powder is ignited, a stream of expanding gas will be ejected through the hole, and you will have created a rocket. So yes, folks, in other words, a rocket is quite literally a bomb with a hole in one end. Or you could put the powder in a tube. You could close one end of the tube and push a projectile down on top of the powder and then light it. And assuming your tube is strong enough, the projectile will be forced out the tube at high velocity, and this is what we would call a cannon or a gun. As I said, the reason that it gets a little confusing trying to trace the history of the rocket is that these three ways of using gunpowder all developed concurrently, and they aren't really described separately in the literature from the time that survives today. But, for instance, there are references and descriptions of fire arrows from the 12 and 1300s, but these use gunpowder, but they appear to use them sort of as an incendiary payload that is delivered by an arrow that is launched from more or less a standard bow. The term does seem to be applied, the term fire arrows, does seem to be applied to arrows that are also launched from tubes using gunpowder as propellant. Now, there is, by the mid-1300s, an unambiguous reference to a sort of multi-stage rocket known as the fire dragon issuing from water, which seems to have consisted of 4 rocket arrows attached to a bamboo tube, which contained 4 more rocket-propelled arrows. As the first set of rockets burned out, it was somehow contrived that they would ignite the second set of arrows, which would then, according at least to the Wikipedia entry, shoot out of the mouth propelled by the gunpowder to destroy the enemy. Now, details of how it was contrived to light all 4 of the initial engines simultaneously, and what happened if they burnt unevenly, and so, in fact, how accurate the weapon ended up being, are not recorded in any source that I could readily locate, but there is no question that it must have been impressive. It's probably fair to say, though, that while there was a great deal of experimentation with rockets in the 12th, 13th, and 14th centuries, eventually the cannon gun application seems to have become the most common use for gunpowder. This would principally seem to be because the developments of science of metallurgy, concurrent with learning about gunpowder. In the early days of gunpowder weapons, the technology for casting large single pieces of metal like a cannon barrel really didn't exist. So tubes or barrels that were used to contain the combustion seem to have been made from hardened paper, if you can believe, or bamboo. These fire lances, as they are referred to, seem to have been pretty low-pressure affairs, initially firing traditional arrows and eventually some form of smaller projectiles, but I can't imagine that they fired them very fast or very far. Given this state of affairs, it was really a bit of a dead heat as to whether using gunpowder to launch a separate projectile out of a barrel, or whether to use it as fuel for a self-propelled projectile, was more effective. But it didn't take long before techniques for making tubes strong enough to contain enough pressure to make the effects of pushing a projectile out of a barrel was just much more lethal and more reliable than the effect of using a self-propelled projectile like a rocket. The trick, of course, is that it actually takes a significant amount of metal to contain the explosive force that is necessary to propel a projectile of any significant size. It also takes a fair amount of metal to dissipate the heat generated so that your firearm doesn't melt or disintegrate after just a few shots. This need to dissipate the massive amount of heat generated by combustion in a confined space is something that we will definitely be talking about a lot when it comes to modern rocket engines. Until the 1300s, the technology of metal production just didn't produce molten brass in quantities needed to cast a gun barrel of any significant size. But by the middle of the 15th century, this technology had clearly been mastered with some truly significant pieces of artillery that began to appear. Also, at around this time, it seems that the processes needed to produce smaller gun barrels that were light enough for a single human to carry, but strong enough to contain the explosion needed to expel a small lead projectile with deadly force, were perfected, and the first personal firearms started to proliferate. Within a couple hundred years, these would become the weapon of choice for organized and even not so organized warfare. So in the end, of the above three uses of gunpowder and its later derivatives, it was artillery and firearms that received the bulk of the R&D spend for the 500 years or so after, from say the 14th to the 19th century. It's true that the rocket continued to get some attention. The British discovered this to their cost, apparently. In the late 18th century, when the Tipu Sultan of Mysore had developed a particularly effective form of rocket artillery that he used against the British East India Company during the Anglo-Mysore Wars. The British were sufficiently impressed and inspired by this to eventually create what was known as the Congreve rocket. This resembled a modern kind of bottle rocket with a cone-topped cylinder full of gunpowder attached to the top of a long stick or pole. While these did see fairly widespread use, apparently, the fact of the matter is that they were both shorter ranged and less accurate than the smoothbore cannon of the day. All of which is to say that by the end of the 19th century, military applications had really not resulted in much development in rocketry from its early days in China. Rockets were still pretty much simple tubes packed with gunpowder with a hole in one end. They were utterly unguided and also pretty inefficient. They certainly bore very little resemblance to the rockets that would eventually take us off this planet. But the existence of these crude rockets was enough to spark the imagination, which eventually led to the birth of modern rocketry. In fact, it's fair to say that the foundations of modern rocketry were inspired not by engineers or scientists, but rather by works of fiction. Writers such as Jules Verne and H.G. Wells looked at the crude rockets that existed in the late 1800s and still managed to envision machines that might lift humans off the Earth. They mused about the possibility of traveling to space and what humans might find there. These efforts ignited an interest in a small but dedicated cadre of scientists, who then worked to build a theoretical foundation on which these dreams of space travel might one day be realized. This culminated in the work of the early 20th century rocket pioneers, such as Konstantin Tsiolkovsky in Russia, Hermann Oberth in Germany, and Robert Goddard in the United States, all of whom more or less invented rocket science as we still know it today. But their contribution will have to wait for part 2 of rocket science, because that's about all the time we have for today. So join us next time for Rocket Science Part 2 as we take a look at how the rocket went from being a thing of science fiction to an engineering fact, and eventually something that is just a part of our normal daily lives. And a reminder that if you're just interested in the general topic of spaceflight, there are lots of other videos to watch in the Terranauts series, including interviews with people who work in space, even if they don't leave the planet, as well as some discussions about things like what it's like to work in mission control and what maybe it must have been like to be in mission control during Apollo 13. So have a look. That's it for now, and we'll talk to you soon.